Well, assignment 9-1, you should have it out. You should have tried to draw the slope fields already for this. There's an infinite number of answers because, as you remember, slope fields model the original function given the derivative. The derivative misses the initial condition, so it could go through any points. So, for example, let's see if I can find my pen. Is my pen here? It's working. All right. Good deal. Okay, so for example, if I just choose a random point, like say this one right here, okay, when I go to draw my slope field, I'm going to follow the slope of that one, follow the slope of the one next to it, follow the slope of the next one, follow the slope of the next. Whoops, that's a terrible, that bump shouldn't have happened. And then it hits here and it's flat, and then it starts going back up. And I'm trying to make it, and it should be symmetric, and it probably isn't because I don't know how to draw. Boom. Especially this cute little slate, which I'm getting better at because I'm getting lots of practice. So there's that, right? And then I could have picked a point up here. If I picked a point up here, this one here, I would have realized I'd gone up there, flat, come back down, look something like this, and something like this. And then, of course, I'm required, according to the problem, to go through the point 0, 0. So the point 0, 0 is down here. So now it's flat down here. I draw flat, and then it goes up steeply. Probably shouldn't cross the earlier one. Looks to me like I should, but whatever. Something like that, right? The reality is I probably should be steeper than I'm currently drawing it, but I drew the other ones too steep, too less steep, so that's good enough. So anyway, there is my slope fields. I got 3 of them. You should only have 2 of them, and that's fine. What's the point? The point is we're now going to figure out how to take this equation. We're going to take this equation, which is dy dx is equal to x 6 minus y. And we want to figure out what the general solution of this is. In other words, what would describe all of these graphs that I've thus far drawn. And so your first thought is, why is this different? I've already taken integrals 100 times. Well, if you look, there's something really bad over there. If I were just to do what we normally do, which is, my pen again. Here it is. If I just do y equals the integral of x 6 minus y dx, I would look at this and notice that I'm suddenly got a y in when I'm taking the integral with respect to x. I don't know how to do that. In fact, we're not going to learn how to do that. What we're going to do instead is we're going to say, I'm not doing that. What we're going to say instead is we're going to look over this side over here. What is going on over here? We're taking the derivative and we're turning it into y by integrating it, correct? Now this side over here picks up a dx, right? Makes perfect sense. That's what's happening here. That's where the integral is happening. And so that's integrating there. What's happening on this side? The dy stays here, and we're integrating both sides. Whatever you do one side, you do both sides. If I'm doing it to both sides, what is invisibly here is a 1, which eventually becomes the y. So the reality is I've been integrating both sides all along. When I wanted to figure out what the original function is given a derivative, I have been secretly on this side of the equation, so on this side of the equation, taking the integral of 1 dy. So we're going to use that exact same property. We're going to say, okay, we can still do that. We're going to go dy dx equals x 6 minus y. And then I'm going to look at it and go, but I want this y to be over here. Now, one of the tricks of this is you have to do it by division, okay, or multiplication. You cannot do it by addition and subtraction because integration and derivatives, by now you should realize, are really connected to multiplication and division. Okay, so when I integrate, I am really multiplying. When I'm dividing, when I'm taking the derivative, I'm really dividing. And so in this case, I take a look at this and go, okay, so to get the y to the other side by division, I'm going to divide both sides by this. This is called separation of variables. So I've separated the variables. Move the y's to one side, the x to the other side. Now I'm going to do what I've been doing all along without thinking about it, and that is I'm going to move the dx over to here, right? So I've got dy is still sitting here like it always has. We just never looked at it. And then over here I get x dx. So now I'm going to integrate both sides. Oh yeah, integrate both sides. Now if I look at the right-hand side, life is easy. That's just 1/2 x squared plus c. Over on the left side, I look at it and there I got a mess on my hands, right? But it's okay because I know how to do that mess. I can set u equal to 6 minus y. Du therefore equals -1 dy. I need a negative, so I'm going to make one. So I set up the integral. The integral would be -1/6 minus y negative dy equals 1/2 x squared plus c. I go ahead and take this derivative and I get negative integral 1/u du equals the same over there. This gives me negative ln absolute value. I'm going to put the u back in. 6 minus y plus c equals 1/2 x squared plus c. So the first thing I'm going to do is I'm going to notice I got two c's in here. And this is going to lead to an interesting problem that only happens in calculus because we're weird. We know these can be any number. Both of them can be any number, right? One can be a 7, one can be a 5. One can be a 3, one can be a 2. We also know, by the way, if one's a 5 and one's a 7, when I move the 5 over to the other side, it'd be the 5 minus from the 7 would be 2. And couldn't c be 2 as well? So this is one of the situations where I would subtract c from c. Subtract c from c. I don't get 0, I get another c, because I don't know this one could be different from this one, right? So I end up with a different c. So I end up with 1/2 x squared plus c. Now that's just the beginning of weirdness with c's. We're going to spend more time with that. Now I've got a negative over here. To get rid of the negative, I'm going to multiply both sides by negative. When I do that, negative c is just, well, it could have been negative to begin with, right? So why would I bother changing it? Now you can, you just don't have to. So I'm not gonna. I got ln of 6 minus y, absolute values. That's really good. Now I'm going to look at this and go, oh, I've got an ln. That's log base e. So I'm going to swing the e across. And I get 6 minus y equals e to the negative 1/2 x squared plus c. Isn't that fun? And then I want to get rid of the 6. And so I get, oh, I still got absolute value bars. I forgot about that. So then I'm going to have get rid of absolute value bars. Remember how to do that? Probably not. That was plus or minus. So I'm going to have to write over here somewhere. Okay, so I'm going to get rid of absolute value bars. So this gives me 6 minus y equals plus or minus e to the negative 1/2 x squared plus c. That's how I get rid of the absolute value bars. Get rid of 6 by subtracting 6. So plus or minus e to the negative 1/2 x squared plus c minus 6. To get rid of that negative, I'm going to bring the negative across, but plus or minus, of course, that's silly. It just becomes plus or minus, so plus or minus e to the negative 1/2 x squared plus c. But the minus to the 6 makes that a plus 6. And so here is my general form of the equation. This is what models everything on this side of the graph over here. Okay, so all these weird graphs I'm drawing, this is it. Okay, now to get the one that looks like that goes through the point 0, 0, get to the one that goes to the point 0, 0, this one that goes through the 0, 0, this graph right here, I need to plug in 0 and check my initial conditions. So I'm going to go ahead and do that. Plug in 0, 0. So now I'm going to go over to the left over here so I can write someplace else. I hope I can find a place to write. Let's go way over here. So I'm going to, if I plug in 0, I get 0 for y. Now again, I'm trying to find the initial conditions. Plus or minus e to that whole thing becomes 0 plus c plus 6. Move the 6 to the other side. I get negative 6 equals negative e to the c. Now I take one look at that and go, wait a second. If I've got negative 6 equals negative e plus or minus e to the c, then in this case, I have to use the minus sign, right? There's no way e to the c can be negative, so therefore it has to be the negative out in front that's causing this. So I rewrite this as negative 6 negative e to the c, and then I remember how do I get rid of the negatives? I just go 6 equals e to the c, and then I recognize, okay, well, that's good, but now I got to get rid of this e. I'm going to swing the e back across. So this becomes ln of 6 equals c. And so for this one equation, this one specific solution, the final equation is y equals negative, because remember we had to use the negative in this case, e to the negative 1/2. Use lots of parentheses when you get ready to type this in your calculator, because that's what I'm going to ask you to do in a moment. Plus, and then I have to type in ln of 6. And then all the way down here I got plus 6. And so I'm going to circle this whole ugly mess. And I'm going to recognize, okay, so now that that's my thing, okay, I'm going to put that in my calculator. And hopefully, if you do it correctly, use lots of parentheses, do everything you're supposed to do, you're going to recognize that it's going to look like this graph right here. And so that is how you take a differential equation. What we mean by differential equations, we mean you have a derivative still in the equation. And so I take my differential equation and turn it into a specific base function or original function or value for the amount. Okay? All right, with that in mind, go ahead and try the problem number 1 on the back, which should be no problem at all. Then try number 3, which could cause you a small pause, and then we will talk together in a moment. All right.